Welcome to the 17th lecture in mechanics of materials. In the last lecture we saw how to solve a boundary value problem involving an axial member. In particular, we saw that the observable strain can be written as delta by L, where delta is the deformation of one of the section points, where the other section point is L fixed. If both the section points move, then it will be delta A minus delta B by L. Okay. And we saw that we use a constellation that sigma axial is equal to E times epsilon axial to solve the problem, wherein we use the equilibrium equations to find the unknown deltas. Okay. So, this is how we proceeded to solve for axial members. We saw axial members placed in series with different area of cross section with different Young's modulus also. You can use the same approach to solve it. We saw how to solve problems involving temperature changes, okay, and then we saw how to solve axial members wherein the property varies across the cross section. For example, we saw a steel casing enclosing a concrete cylinder, how to solve the boundary value problem involving that, how to write the strain compatibility condition, and then how to proceed to solve the problems what we saw in the last lecture. In today's lecture, we will solve another boundary value problem, which is beams. It will take us 2 or 3 lectures to formulate what is the displacement, what is the, how you go about solving problems involving beams. Okay. In particular, we are interested in solving this problem. Say I have some 3-dimensional body. For example, I am taking a square cross section subjected to some loading, arbitrary loading, and there are some support reactions also coming in, which may be here. I am assuming it is simply supported. Okay. The idealization of this beam would be, as a 1-dimensional member, would be something like this. Okay, wherein this is the arbitrary loading that the beam is subjected to with a simply support boundary condition like this. Okay. This load is distributed uniformly across the thickness of the cross section. Okay. Across this dimension, the load is uniformly distributed, but the load can vary across the length of the member. Okay. Along the axis of the member, the load can vary, but it is uniform across the width of the cross section. Okay. So, this loading is given as load per unit length. This load denoted by Q of y is given as load per unit length. In particular, if you are looking at the stress components, Qy would be integral sigma yy into dz 0 to b. If I take my coordinate system as the following: x, y and z, and the rectangular beam is yz, a cross section is given by b, and this is given as h. This integral will be minus b by 2 to b by 2 in this case, because I assume the origin to be at the centroid of the cross section. Okay. So, this will be minus b by 2 to b by 2. Okay. We will see all this in much more detail shortly. Okay. Now, what I want to do is, when a structure is subjected to this arbitrary loading, I want to take a section at some point. Say I want to take a section at this point, okay, and then expose the traction and write the global force equilibrium and moment equilibrium to find what are the resultant traction that is acting at that cut surface. Okay. So, basically what I want to do is cut there. So, let me take a plane section, okay, subjected to some arbitrary loading. Okay, subject to some arbitrary loading like that, and here at this cut surface the traction will act not necessarily parallel or perpendicular to the plane, but it can have an inclination. For example, here it might be like this and then it might have an angle like that with the magnitude much smaller, and then it can change direction from there to something like this, okay, and finally it can have orientation like this, okay. So, the traction we will see changes like this across the depth y of the cross section, okay. So, the traction will change across the depth of the cross section both in magnitude and in direction in a general loading case. We want to find what this traction T is of E x is, because normal to the surface according to the assumed coordinate system is E x, okay. So, now let us assume a general stress state. Let us assume that the stress is given by sigma xx, sigma xy, sigma xz, sigma xy, sigma yy, sigma yz, sigma xz, sigma yz and sigma zz, okay. That is a general state of stress. For this general state of stress, what will be the traction T's of Ex is what I want to find. T's of Ex would be that stress acted upon by 1 0 0, that is the Ex vector. Stress is symmetric, so I drop the transpose, or else I will have a transpose there, okay. So, now this will result in me getting sigma xx Ex plus sigma xy Ey plus sigma xz Ez, okay. So, what happens is in this cross section the traction can vary from point to point. It can have a 3-dimensional inclination like this, okay. It can have a 3-dimensional inclination like that, wherein there will be a horizontal component which is sigma xx, the vertical component will be sigma xy, and the component along this direction would be sigma xz, okay. So, that is what we get. This is what we saw even when we were interested in drawing the stress cube and things like that, okay. So, we got the traction to be this. Now, I am interested in what is the net force acting in that cross section, okay. I am interested in net force F, which is integral T's of Ex dA, okay, where this dA is nothing but dy dz. This is the area integral. I have to integrate this over dy and dz, then I will get this as integral sigma xx dA Ex plus sigma xy dA Ey plus sigma xz dA Ez. Now, this we write it as the axial load P times Ex plus the shear force Vy acting along Ey direction plus the shear force Vz acting along Ez direction. This is the force vector, net force vector acting because of that exposed traction. In other words, again going back to the section, I have this section, the net force acting on this surface is P, Vy and Vz. These are the net forces, where P is given by integral sigma xx dA and Vy is given by integral sigma xy dA and Vz is given by integral sigma xz dA. You can note that the second index is what is the suffix for the shear force Vx and Vy and Vz, okay. Now, the traction were to act uniform across that section, then you will not have any moment when you take it about the center of the cross section, okay. On the other hand, the traction is not having a uniform magnitude not direction. So, what is going to happen is there are going to be 3 moments that are produced due to this traction. Okay. So, let us compute the moment due to this traction. Net moment m is given by integral r cross f, f is T's of Ex dA. This if you recollect, it is a cross product. Okay. So, now what is R? R is, let us assume it as, R would be for any point in this cross section, what will be R? Say this distance from the origin was x naught, R would be x naught Ex plus y Ey plus z Ez. Okay. Recollecting that the origin was from here, this is x, this is y and this is z. I have r given by this expression here, and T's of Ex we found that is given by T's of Ex is given by sigma xx Ex plus sigma xy Ey plus sigma xz Ez. So, now r cross f moment would be, you have to do the determinant of this Ex, Ey, Ez, x naught, y and z, sigma xx, sigma xy, sigma xz. It is a shortcut, but that is okay. So, this will be sigma xz into y minus sigma xy into z into Ex plus this integrated over dA plus sigma xz into x naught minus plus sigma xx into z Ey dA plus integral sigma xx into y minus sigma xy to x naught Ez dA. Okay. Now, this I will rewrite it as the torsional moment T times Ex. This is a moment acting along the axis of the member, that is along Ex direction, plus my moment minus Vz into x naught. I will explain shortly why this comes about, plus mz moment minus Vy, no, I left a negative sign here, this should be negative minus plus Vy into x naught into Ez, where T is integral sigma xz y minus sigma xy z dA, my is integral sigma xx into z dA, and mz is, I want to write with the negative sign. So, this will be minus integral sigma xx into y dA. Okay. Now, this x naught is a constant. So, since x naught is a constant, integral sigma xz x naught dA can be written as x naught into integral sigma xz dA, which will be x naught into Vz. From the definition that sigma xz dA is Vz, coming from this definition we write this as x naught into Vz, and similarly we write integral sigma xy to x naught dA as x naught into Vy. Okay. So, we got that the moment is given by this expression. Let us proceed. Moment m is given by T's of Ex plus My minus Vz x naught into Ey plus mz moment plus Vy into x naught Ez. Okay, where this T is called as torque or the component of the moment acting along the axis of the member. We will come to this after we finish the bending moment expressions. The other two, My and Mz, are called as bending moments. Okay, that is acting not along the axis of the component of the moment, not along the axis of the member, is called as bending moments. In particular, Mz moment will produce a bending like this. This is Mz, right? For a coordinate system, we had the coordinate system as the following. We had Ex, Ey and Ez oriented like this. So, the moment Mz, which is this moment, the moment Mz, which is this moment, will produce a deflection along the y direction. Similarly, a My moment is a moment acting like this, a moment trying to bend a member like this. Okay, that moment is My moment and it will produce a deflection along the z direction. When you bend it like this, it is going to curve like this, and that is the displacement along the z direction. Okay, whereas the torque is not going to produce a displacement normal to any of the axis, but what it is going to do is it is going to produce an angle change. Okay, the torque is along the axis of the member. So, what happens is it produces a shear stress, or the shear stress causes the torque, which produces an angle change in the member. Okay, so that is why we are not interested in the torque right now, we are interested in the bending moments. Okay, you can see the bending moments are dependent upon sigma xx, bending moments are dependent upon sigma xx with the corresponding lever arm being either y or z. Okay, so sigma xx, the normal stress sigma xx is the cause for both bending moment along y and bending moment along z directions. Okay, okay. So now then what is this term Vz into x naught and Vy into x naught doing here? Basically, if I have to, this is finding the moment only due to the cut surface here. I found the moment acting on this cut surface, wherein I have this forces plus now 3 moments acting on this cut surface, right, plus I have 3 moments acting on this cut surface. I will indicate the moments by double arrows. This is a torsional moment, this is a Mz moment, and this is the My moment. Basically, the direction of my thumb points to the direction of the moment. If a moment is bending like this, my thumb points the z direction, so that is a Mz moment. If my moment is bending the beam like this, my thumb is pointing the y direction, so that is a My moment. Okay. So basically we understood that the cut surface produces some force and some moment in the body, okay, because it is not uniformly distributed.